Hi guys, so this is the video about momentum and impulse, chapter 9, and I don't think that I can explain everything that we have discussed, but I'm gonna go through a little review. So the momentum is given by mass times velocity, and the fact that it is a velocity, we know that it is a vector. So momentum is a vector, and we are using the letter P for momentum. And then the force and momentum are related in the following form, where you have dp by dt equals to F. So if we have a momentum where it is a function of t, by taking the first derivative, we can find the force. So that's the second thing we learned. So basically, by looking at the two equations that we have here, we can find out that the units of momentum can be given by kilogram meter per second. That is from the first equation from here, kilogram meter per second. And the second equation suggests us that the momentum is Newton second. So basically we can use either of those. It is easier to use Newton second, so we will be sticking to that. And then on the other hand, momentum is related to impulse. So impulse, the letter symbol we are using here is J. J equals to F delta T. Now when I am writing impulse in this form, there the F is a constant. Not only that, the F is actually the average force exerted on the object. We discussed about collisions that happens only for a very short period of time, and this delta T is basically very small, in the order of milliseconds. And then here the y-axis is force, and the F average is what we are using here in the equation. So I am going to write this as F average, and I am going to change this also into F average. So this is the average force. And then if you have an impulse which is for example, if you have a force that is a function of t, then we no longer can use this equation. We need an integration to find the impulse. So here we are doing an integration going from 0 to t, whatever the lower and upper limits are given to us, and then you will get the impulse by doing an integration like this. So both of these equations are important. If you have a constant force given to us, then you can use the first equation, and if the force is given as a function of time, then we are going to use the second equation. And then yesterday in the class we were discussing we discussed a couple of problems, and one of them is the bullet hitting and like a block that is hanging, and at the beginning it is stationary. You remember that, and that was the lab that you guys did, and it is called as the ballistic pendulum. And I'm going to draw a quick picture here because that problem is an important problem. So here you have a very small bullet with a velocity, I'm going to call it VB, and there is a hanging block, wood block, and this was basically what they used in the past before the electronic systems were present. This is what they used to find the speed of a bullet back in the day. So we are doing the calculations here, assuming that the bullet velocity is unknown. And I'm going to take this as the block, and V block at the beginning, this is 0. And I'm going to draw another picture here, and this is sort of like an intermediate position. And at that point you can see that the bullet is embedded inside the block, and this has created a system, and the system is called as the block bullet system. Now we can use the conservation of momentum for this problem. And when I am doing that, I will tell you what conservation momentum is. Now, as we discussed in energy, the conservation of momentum also has a similar form where you have an initial point and a final point, and we are looking at the same system. First we are looking at the bullet and the block system, and the second also we are looking at the same, but the difference is first time the bullet is outside, the second time bullet is inside. Now after the collision, of course, this is not going to stay, the block bullet system is not going to stay at rest, and I am going to call the final velocity as v. So let's look at the conservation of momentum. P initial equals to P final. Now the initial momentum, in order to find the initial momentum, we have to look at each object. So we have two objects. One is the initial momentum of the bullet, little b, and the other one is the initial momentum of the block, big B. And they both are for initial, so I am going to use that letter I. And then after that we don't have two systems, we have only one system, and I'm going to call it block plus bullet system, and the momentum of that, which is the final state, block and bullet system together. Now I am going to substitute for each, and the first one is the bullet, M of the bullet and V of the bullet. Now that is the most important piece here, because that's what we are looking for. And then the second one, we have mass of the block and the initial velocity of the block, which is a 0. We will plug that in later. And then we have the block and the bullet, where the mass is mass of the bullet plus the mass of the block times v, where v is the system velocity after the collision. Now if we plug the numbers in, we don't know, MB was given in the problem, so you can substitute for that. But here we don't, we know that the initial velocity of the hanging block is 0. And then this side you have mass of the bullet and mass of the block times V. That's all we can do here. So I'm going to rewrite the equation, removing the 0 from our equation. No point of having that in the equation. So you have the mass of the bullet, mass of the block times V, and this is our equation number 1, and there's nothing else we can do. I'm going to just put check marks for the things that we know. We know the mass of the block, we know the mass of the block and the mass of the bullet, and we don't know V or VB. Now the problem continues, and I am going to go up back to the place where we were, and I'm going to draw the next part. Now after the bullet is hit and when it is embedded, then the system starts swinging, because when there is a non-zero velocity, that's what happens, right? So the system rises up to a certain height. Now let me take this as H. Now I am going to take it to the other side, and I'm going to draw a little line here. And now I am going to call I'm using a different color here, and I'm going to call the final position that I listed for the collision as the initial point for the energy conservation. Now we have discussed multiple questions on this form where you have the energy initial equals to energy final. We don't have any springs attached here. So it is basically the kinetic energy of the system initial plus the potential energy of the system initial and the kinetic energy of the system final and the potential energy of the system final. So basically that's what we have. Now kinetic energy initial, let me substitute for that, 1/2. Don't forget we have the block and the bullet together, so we have to substitute the full mass there, and the velocity at that point is v, same v that we had earlier, V. And then the potential energy at that location is 0 because we take this point to be our 0 potential level. And here you have 1/2 mb plus mb the block, and then 0 is our velocity at the highest point, and then we have the potential energy equals to mass of the block, mass of the bullet, mass of the block times g and h. Now you can see that one thing is common here, and that is the mass. So we are cancelling the mass. It doesn't matter whether it is a 0 there. It's like, you know, it's common everywhere. Now the equation reduces so much, and that what we have here is 1/2 v square on this side, and the other side we have g h. So you guys have the velocity equals to square root 2 times g times h. Now if the height is given in the problem that we discussed in the class, the height was given. If h is given, then you can find v, and once v is found, you can substitute it in the equation here in equation 1. So I am just going to use the v that we have up there and then write the final value for v bullet and then complete the problem. I don't have any numbers here, so I'm gonna leave it like that. But when the problem is given with numbers, you should be able to complete that. So there you have 2gh, and then the bullet velocity or the bullet speed is given by mb plus m block square root 2gh divided by mb. Now if someone is thinking of writing this in the equation sheet, unfortunately this is not allowed, mainly because this equation only works for one type of problems. Like, you know, if you don't, in order to use this problem, you have to memorize the problem as well. I mean, in order to memorize this equation, you have to memorize the problem as well. Otherwise, this is not a common equation that you can use anywhere. And then the second thing that we discussed was a collision. And there we were looking at the momentum and then change in momentum, forces, and the impulse. So the collisions, the problem we discussed in the class was something like this. There's a wall and a driver comes in with a certain velocity. We can take this velocity as 70 meters per second, and then after the collision bounces off and creating an angle 10 here, and this angle is 30. So the first part of the question asked us to find the impulse, find the net impulse, and then the second part of the question asked us to find the average force exerted on the driver. So the driver's mass was given to us, I think it was 80 kilograms, something like that. And in order to find the impulse, we can use two different equations. The first equation, J equals to mass times V final minus mass times V initial. In other words, P final minus P initial, change in momentum. But we know that J is a vector, momentum's vector as well. So we might have to find x and y components. It's not might, we have to find x and y components of J. So Jx, Jy, we have to find those, and then we can find the net using that. Now at this point you should be very comfortable with these equations, because we have used this equation uncountable times from the beginning with different variables. First it was velocity, second it was acceleration, third it was force. So it was a continuing equation, right? Now the most important thing here is finding the velocity components, because in order to find the x component impulse and the y component impulse, you need to find the x component velocity and the y component velocity. So initial x component velocity is 70 cosine. Now we have to find out what the angle is. Now in the class I was very clear about these directions. So the direction here is pointed toward the center. Now when something is pointed toward the center, we have to always make sure to extend it and then point it away from the center. So this line is pointing away from the center. That means the direction is actually 30 degrees with the positive x-axis. Now V initial x therefore is 70 cosine 30, and V initial y is 70 sine 30. V final x component, that is this, so that arrow is already pointing away from the center. Center is over here, and as long as it is pointed away from the center, all good. So if we take that final velocity to be 30 meter per second, I think these are the values we used yesterday. So if we do that, then we have 30 cosine negative 10 and 30 sine negative 10. That's for V final y. Once you have V final x, y, V initial x and y, then you can find the x component of the impulse by substituting them. V final x component minus V initial x component, and there V final y component minus V initial y component. And after you find the values, the numerical values, you can plug it in the equation here to find the x net component impulse. Once you find the net impulse, to find the force, we can simply use the second equation we learned in the class for J, and that was F. Actually, this was the first equation we learned in the class, and F average delta T, and the delta T has to be given something like 14 millisecond or 10 milliseconds, something like that. So here you have 14 times 10 to the negative 3, and that is in seconds. And using this, we can find the force. So you can substitute net J from the equation over here, and in that case what you don't know is the average force. So the average force can be, F average can be net impulse divided by, I used 14 milliseconds, so that's that. So you can see a large negative power in the denominator, so you're basically expecting a large F average, and the unit is newtons. Okay, and that's about it. So both of these are good questions, good problems, and I have posted some problems from the book chapter, and some of them are directly related to these two problems we discussed.